For the next part of homework 5, we're going to be simulating our closed loop response of our third order process. And what we're starting with is our GC, which in this case will be 1, which we will adjust later to find our ultimate gain, and our process 2 over 12 times s plus 1 to the third power. And then we will be combining these into one process, which we will call G, which will just be our GC times our GP. We will also need to have our W imported, so we can substitute our S for omega J, which we did in our last part. So to do this, we'll call it our G JW is going to be equal to simp dot lambda phi lambda phi we want our W, we want our G dot substitute, we want to substitute our S for W times J, so WJ, and then we also want to have our scale for this, which is going to be a logarithmic scale. So we'll call our W's, it's going to be np.log space from -2 to 0. We want 100. Gotta spell it right. Log space. We'll do this for our values, WS. So the next thing we need to do is we know that we set our i's and our r's to be equal to sines and cosines with phase lag, and also we derived that our m, or our magnitude, is going to be equal to our I squared plus r squared, square root of that. So what we need to do is take our i's and our r's is going to be equal to np dot imaginary of our gjw, and then our r's will be equal to our np dot real of our gjw. Now what we can do is we can get our m, which is our magnitude, which is going to be equal to np dot square root of I squared plus r squared. And then lastly, we just need to get our phase lag, which in this case is going to be equal to, or our psi will be equal to np a tan 2 of our I divided by r, so I and r. So now we can look at our m and our phi. As you can see, we have our values. So now what we need to do is we need to plot this out and see what this tells us. It's important to note that we get this back in radians, and we need to multiply it by 180 divided by np.pi, and then this will exceed the value of 180, which it will just return back to 0. So we need to np.unwrap this in order to get the true value. So then we can make our subplots. So our figure, make subplots, rows, we'll go rows equal 1, columns is 2, and then fig dot add scatter. We want our x to be our w's, our y will be equal to our magnitude. We'll put this in row 1, row 1, column 1. So there's our magnitudes. And then we want to fig.add scatter. We want our x to be our w's, our y to be our phase lag. This will be in row 1, column 2. Why isn't it getting unwrapped? Name m name does this need to be outside? That looks better. Okay, so the next thing we need to do is fig dot update x-axis, type is log. This is in row 1, column 1, and then we need to do the same thing for row 1, column 2. Okay, so now we can see that at our phase lag of 180, so that's about 0.14, we are going to be at a magnitude of 0.14, 0.26, meaning that we can increase our controller to be more responsive. So what we can do is this. Well, I guess first we can plot this out in terms of our closed loop. So our GCL is going to be equal to our GC times GP divided by 1 plus GC times GP. Our time and our Y values will be equal to our simulation of GCL. Our lambda t is 1. Our n will have 1,000 time steps, and our dt will be 0.5. And then our fig2 make subplots. Don't need any of that. And then our fig.add scatter. Our x's will be our t's. Our y's will be our y. And our name will be GCL. Hello? Oh, fig2. Okay. So as you can see, that is our simulated closed loop response. And now we can adjust our GC to find what our ultimate gain would be. So because this will just multiply it directly up and down, we can find what we're at. So about 0.026. We know that number needs to be below 1 in order for our system to remain stable. So we can test this out. So if we make this 3, it should end up closer to around 0.7. Get me out of here. So now we need to see where our phase lag's at 180. So between 0.1 and 0.848. So we find that point here. So our current magnitude is somewhere between 0.78 or 0.7 and 0.78. So we know we can increase this more. As you can see, there should be a little bit less stability here, but it eventually comes back. So now if we make this 4, we should see that at our 0.14, we should be close to 1. So we're between 1, 0.04, 0.9. So this should be getting close to unstable. As you can see, that is true. And if we were to go any higher, we can see our system quickly becomes unstable. So we'll go back to 4. And that is what we have determined to currently be our ultimate gain. And now we can use our methods to determine what the most optimal values for our PI controller would be. We can now use our Ziegler-Nichols method to determine what the optimal values for our PI controller would be. So our K ultimate we know is around 4. Our integral ultimate is going to be the distance between our humps, or our amplitude frequency, which is about 45, closer to 44. So say 44. And then we know our Kc will be equal to our K ultimate times our constant from Ziegler-Nichols, and that our tau I will be equal to our P ultimate times our other constant, 8. And then our new GC is going to be equal to Kc times 1 plus 1 over tau I times S, and our GP will remain the same. And then our new GCL controller is going to be equal to GC times GP divided by 1 plus GC times GP. Now we can simulate this again. Also, same thing here. This needs to be figure 3 now. Figure 3. And GCL controller. And this needs to be GCL controller. So we can see here is now this is what our optimal controller response looks like for our third order system.